Hi all, this is Claudio from expertfea.com with another live stream in ANSYS workbench, mainly the drilling of soil using a Tricone drill bit. Let me share my screen and you'll see what I'm talking about. I was talking about such drilling, Firstly, a short reminder about our website, where you can find lots of simulation tutorials, books, live FEA support, and so on. Very useful for your FEA work. So a little about Tricone drilling, something like this. As the name says, it's a drill with three, let's say, sub-assemblies, teeth sub-assemblies. It's pretty common in drilling and boring. So this is what we're going to analyze today. Of course, using the only mesh that is suitable for this, for the lots of debris. And I'm talking about particle bodies and SPH, or smooth particle hydrodynamics. On videos, and maybe we can see here, for example. This is what we're aiming to do. We're aiming to do, however, here is the cleaning fluid, let's say, designed to remove the debris simulated, but we're going to do the structural part, where these teeth will dig up into the soil, into the rocks. So you can easily find such geometries on GrabCAD. I only downloaded them, and together we're going to look on these geometries. So I open Space Claim, and here let me drag and drop what I downloaded from GrabCAD. For example, there is this thing, Tricone drill bit. Let's see if it suits our topic. Oh, it looks very nice. Very nice. Let's make a section view out of curiosity to see what we have inside. With the control pressed, I'm hovering here, and section mode. It has like a bearing here. All right. So in order to simplify these, I will remove the balls and leave only the. I will also remove this gasket or whatever is this. This has the purpose in order to prevent debris and rocks to enter this subassembly. I will also delete this. Only what are important here are the teeth. I don't understand what is the purpose of this. It's from the teeth that are sectioned or hidden here. Okay. So let's simplify them. I would also like to kind of get rid of all these rounds in order to have a more coarse mesh. So do we need these balls? I don't think we need them. Let's see if I can suppress now or delete them. Yeah, they are patterned. Super. Another question is, can I? Yes, I'd like to delete all of them, because I would like for the teeth to merge the teeth into the support, into the fixture. So let's delete these holes. Hopefully they get deleted everywhere. Let's see. Oh, no, it's not deleted. Selection equal radius cylinder delete. Fail to remove face. All right, let's avoid it for the moment. Equal radius cylinder delete. Okay. So here it seems like it's a little tricky. Hide. Let's try with this selection. Does it work or not? No. What is the problem? We can use another part, no problem. Let's delete these. Let me first delete one ball, and hopefully all the others are yes, all the others I did it because we don't really need the we're going to work with a simplified version. What's up with all these knurls from? Let's see if I can delete them. Come on. Yes. Dear knurls, get out. And these ones. All right. Right click show all. Let's see if I can kind of copy paste this. 1, 2, 3. Control C, Control V for the copy paste, and I am going to kind of something like this, kind of move it here, and I will assemble it. Let's see, how would I assemble this? For example, the first thing, assemble a line. Yes, and now what is the distance from here to here? 2.5 millimeters. By the way, we need to resize this. 2.5 millimeters. All right. Let me kind of align this with this. Let's see if it's possible. No, the other way around. I will firstly select this face, then this face, align. Then I will make like an offset, 2.5 offset. All right. Out of curiosity, can I move this with 2.5? Move. I will select this anchor according to one of the cylindrical faces and just move it with 2.5. And that's all. All right, so I have everything. Everything is needed. What I would like to do, of course, we're not using fluid to remove debris. Like even for let's make like a section view if possible. It's not possible. We're going to remove this channel from the side, but right-click delete empty components, right-click source internalize all, and we're going to save this. Tricone drill bit, v1. All right, let's see if we have any question from the large audience. No question. All right, here we do have some thread or whatever is this. Let's attempt to delete it if possible. Oh yes, it's possible. And is it so easy? Oh, it's so easy. We like space clean very much. Can I select this, for example? Just asking. It's so easy. Please adopt this modeling software if you want to make your life easier. Your life will definitely change for the best after you adopt space clean. Believe me. I don't need this. I would need a reference to create a rotational joint, but I don't think this axis is aligned with this axis. So yes, they're not aligned. My idea is, can I delete this? Can I? Let's see. Yes. There is also the possibility of select, right-click, select depression, and delete. Yes. Again, right-click, select depression, and delete. This is useful for shrinks or psychiatrists. This is how. This is the easiest way to cure depression. Right-click, select depression. Right-click, select depression, and delete. All right, we're on the very good path. Can I delete this round? Just asking. Yeah, let's see if it's possible. It is possible. Oh, such a nice 3D model from our designer colleagues. Double click, delete, delete. Do I have any separation here now? Okay. Yes, it looks very nice. Control S to save. And is it possible to delete these rounds? Just asking. Selection. All rounds, whatever is written there, and delete. Oh my God, we are absolutely spoiled with such grace, because everything was perfectly. What are these faces? Can I delete them? Yes, but will they be deleted on all the parts? Yes, perfectly. Oh, something that works perfectly from the very beginning. This is a rare moment in the life of a net analyst. So now, let's save. I would like to make this part transparent to understand what's going on inside. I do have a radius for which I don't care too much, and here there is a radius. Do I leave it or not? You know, I would also like to get rid of this radius. Oh. Not so fast. Because if I delete it, look here, then it will get disconnected. So let's cool off. Can I please delete this? Yes. Transparent. Hide. Delete and hide this. Double click. Delete. All right. And I was wondering, what about deleting this chamfer? This one, and this one. Then let's leave everything else. Also, let's make this transparent just for fun. Do I need to delete this these two round faces where the balls used to be, the bearing balls? Let's see. Hide others. With control pressed, I can kind of hover with control pressed. Delete. And the third one, which has the round, is this one. This with control pressed, delete. Yes. They look very nice. Now, I was wondering if I should make like a gap or allowance between these shafts and holes. I'm wondering this. These initial bits are too... They're colliding between each other and also with the fixture. Control S to save. All right, we have this option, prepare interference, and let's look. Besides the teeth will clearly interfere. Other interference. No other interference. Oh my God. The question is, will we allow the teeth to dig into, to carve out the fixtures, the three fixtures, or we will cut out the teeth? Let's, of course, let's let the teeth be untouched or integral inside these fixtures. So now we have this annoying whatever is this, and because it's patterned, okay. Or in order to get rid of all these small faces here and on the bottom here for each tooth, let's undo. And I was thinking about merging the teeth into their fixtures. All right, so escape, and let me hide the main fixture and other two. For example, let's go for design, combine, and we'll have a single part here. Look here, it looks so nice. One part. All right. So we repeat for the other way. Look here, it transformed from a sub-assembly into a single part. Come on. I said, come on. No, you don't want? Okay. Yes. Let's merge them. If you select all of them from the right to the left, they will merge very nicely. right click, delete entry components. And the third one is this one, delete entry components. All right, let's hide this one. From right to the left, combine. And it will automatically merge. This is a very simplistic way and easy way to model, and it will leave us enough time to focus on the simulation. Right click, show all. Let's see if I can get this. All right, put it here, delete this subassembly, and this is the main frame, the main branch, the main fixture. All right. This would be nice. All right, let's kind of design the hole, the soil to be drilled. Something like this. Sketch mode, and let's look from this side. Do we start with the rectangle? Why not? Let's start with the rectangle. Yes. So 3D mode, and here how deep will we drill? I would be happy if we can drill 150, or this portion, a third of the tool. If we can drill this, then it would be extremely nice. Let's see if it works. I'm wondering, how do we fix this? This will be a particle body, and usually the particle bodies cannot be clearly fixed. They need to be held by something. Let's see. So you know what? In a predicting manner, preventive. Let's make this a little bigger. All right, and let's kind of model something like a frame. Control C, Control V to copy paste. And we have, what is this? We don't care. I care about this, because I would like this to be what did I do here? Control C, Control V. All right. Let's name them a little. Soil. This is the main frame, whatever. Teeth 1 for lack of inspiration. Teeth 2. And this is, of course, teeth 3. All right, and this, I would like to pull it out for a little, just a little, you know. Let's see how much. Something like this. This will act as maybe as a holder or fixture. You'll see when we go in ANSYS Workbench. Fixture or frame. I will call it frame because we might need this to define as having a bonded interaction with this part. Because from my experience in the past years, this cannot be fixed. Yeah, we'll have small spheres which cannot be fixed. But it allows the SPH body, it allows to be bonded to a Lagrangian, a meshed body. Meshless body can be bonded to a meshed body. Control S to save. Yeah, this is kind of all. We're going to rotate this, yes. Let's keep it open. I opened the ANSYS Workbench and I will drag and drop an Explicit Dynamics scenario. Let me see if there is someone in the audience. No, of course. No problem, because we like silence. Let me copy paste this geometry that I just created. Control V here, and let me save here as stream 19 March what, 5th. Tricone drilling soil and SPH. I will write here. Tricone drilling soil SPH. It's a mouthful, but we will survive, no problem. Do I take this one opened or the other one, or import geometry, browse? Let's take this one. This means we can close basically, because it has no connection with what I have on my drive, on the other drive. All right. So, ladies and gentlemen, let's start with the FEA. I need to define the materials. What material are the Tricone drill material? Drill bit material, all right. Heat-treated alloy steel for strength and fatigue resistance. Tungsten carbide inserts. Oh my god. It depends on the rocks, on the hardness of the soil, of course. So I said, let's double click here and insert something. Delete, yes, and here we have general nonlinear materials. I would like to use from here structure steel nonlinear. And geomechanical materials, if it works. Let's see if it works. For example, limestone or sandstones. Let's see. So F7 for a full screen. teeth. These are structures still nonlinear. Let me make the main rigid and the frame. Let's make them rigid. Rigid and structure still nonlinear, and the soil, let's go with limestone at this moment. We don't care about the contacts, but what will happen will be something like this. Now I'm seeing that there is some interference here. And ANSYS didn't tell me anything about this interference. All right. Let's solve this interference. Anything? Nothing. Okay. So because they need to kind of mesh together to synchronize the teeth, so for the teeth not to collide, I was thinking about not allowing these 3-toothed tools. I would not allow them to touch each other, only to touch the soil. So we have, let's see, where do we have interference? Somewhere there is interference, maybe here. Yeah, we don't care too much. Prepare interference. Yeah. There is interference, but only here. What do we do? And let's remember to scale this tool. I forgot about scaling it. All right, firstly, I do have these faces which I would like to disappear. Oh, no. All right, and faces with same area. Let's see. Yes. No. Selection. Come on, please delete, please. I would like to avoid having small elements during the meshing procedure. Okay, perfect. So regarding that interference, how should we solve it? We just remove it, okay? Yeah, let's not care too much. Subtract from smaller body from larger body. Let's subtract from smaller body. You know what? Let's cut from the teeth. Something like this. Anyway, we'll not care because we'll not allow interference between these parts. The teeth will not touch each other. So right-click source, internalize all, right-click delete empty components. File save as. I would like here to write V2. All right, Control S to save, and here on the geometry, update geometry from source. It goes pretty fast because space claim is opened. Perfect. Let's close space claim. Now, do we have these? They remained rigid. All right. I don't care about contacts. You know what? Let's see if we have a mesh. This is very important. Quality smoothing low, capture curvature no. It's kind of too coarse. And let's see if it will mesh as particle body. So here we need to go for method, click the soil part, and choose particle here. Let's leave default, generate mesh. Yes, it's getting meshed. This is the only way to properly erode, to drill and bore soil. I'm talking about using SPH body, particle bodies, yes. So I like having coarse mesh because it will ensure we have around 30,000 nodes in total. It will ensure that we have a faster solving time. Now, let's go and assign a minimum size, let's say. I keep saying that I will scale the assembly, and I forgot it. Let's scale it. Do we have a dimension? Drill bit dimension. Click on drill bit sizes. Of course, in feet and millimeters, finally. PDC bit breaker, 240 something, this kind of the diameter, I think, 400. Metric. Why do I bother with writing? Oh, yes. 400, maybe, what is this? The main 400 millimeters, all right. So, for example, this diameter is 62 to be 400, 7 times. Let's resize everything 7 times. Anchor point, and we are resizing 7 times. Look here. In principle, we should have a diameter or radius. Here is radius or diameter? Size. It's not possible to write size. You should write something. Radius or diameter. Come on. Size. Size. Control Z, and I will resize it 5 times. Okay. Yeah, let's. It's a custom drill. In this tutorial, we don't need to give account of what we're doing. This is a proof of concept, you know. Geometry, all right, they remain here. Mesh. So now we need to think 5 times bigger. 70, maybe 60 here, which is 4 times. Let's see. All right, we're approaching. And this one, 80,000. Oh my God, 80,000. Come on, why don't you want to mesh? Why? No problem. Instead of no adaptive sizing, let's choose yes. Here, resolution 2, transition fast, right click, generate mesh. How is this called? This one. I'm wondering if it's this one. So it's between X and Z. You see here, between X and Z. And here is, so it should correspond to this one, if I'm right. There is also other method of kind of healing the geometry. Maybe medium here. Right click, generate virtual cells. Hopefully they will heal what we need. Yes, not today. All right, let's take 60 and force this one. It is X and Z. It is this one. X and Z here. And here, where do we have the global coordinate system? It's here. Let's kind of match what we have in SpaceClaim with what we have in Workbench. All right, here and here. Something like this. So the one that it doesn't mesh is this one along the z-axis. So it's clearly this part. Just to keep this in mind, okay, it's this part. What I can do is assign the feature size bigger than the default. The default is how much? We cannot see it. Let's choose 5, for example. What do you know? It just works. All right, we can get started with the boundary conditions. What I told you, for example, if I'm going to suppress this body, Control S, let's see if I can assign a fixation. Fixed, you see? Control F. Let's see if I can assign a fixation on the particle body. It's not possible, you see? This is the particle body, and we cannot say it. Let's try and fix nodes if possible. Will it be possible? Let's see, I don't know. I don't think it will be possible. For example, can I select these nodes? Also these ones, and these ones, and these ones. Ah, no, they're not selecting nodes. All right, so mesh, display. There is here a nodal displacement, and I'm thinking about making all displacements 0. Let's see if it works. Delete. Let's see if it works. So, nodal displacement. It chooses a name selection. All right. Can I change cursor mode to node? Let's see if it works. Yes. And here I was thinking about pressing N to create a name selection. I will write here nodes. This is the name selection. These ones, they should be more, I think. We don't care too much. Let's see here. Yes. Does it work or not? 0, 0, 0. Oh, we might be onto something here. All right, so I was thinking about having a body ground revolute joint for this face. Change the selection to single select. Change cursor mode to face. And I would like to rotate this main fixture and assign the rotational joints between. So body revolute, and we have this on one side and this on the other side. We have one revolute joint. Body revolute, again, this on one side. Hide this on the other side. I'm talking about reference and mobile. And the other thing, body revolute, the same. Reference here, hide the part, click here, yes, show all. And these are the joints. One revolute here, absolute and relative here. Tick, 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 yes. Let me delete the default interaction, the default frictionless interaction, because I would like to assign them custom, let's say. For example, body interaction. I would like to have control. What is the friction coefficient between steel and soil? Friction coefficient. How much? Internal friction. Oh my God. 0.35, 0. You know what? 0.42 would seem very well. So, Control B. I would like to have the interaction between these three as frictional 0.42. This is one thing. And what else? Nothing else. I can assign another interaction between these two if I predict that some of the debris resulting falling parts will touch this frame. Why not? All right, so body interaction between these two, the same thing, frictional 0.42. So I avoided to have a contact. Yeah, I don't have a specific contact between these two. They will engage. This will rotate because I defined the three joints. Yes, these ones. And this will rotate due to the absolute joint that I defined here. But there is no contact between these two. These three, they will not touch one to each other. One second. They will touch, because I didn't assign pairs. Let's discretize even more. So, body interaction, this one and this one. (0.42). Body interaction, this one and this one. Frictional 0.42. And the third one is the one that is behind here. Yes, 0.42. So now we have only the interaction between the frame and the resulting debris, and each tooth part with the soil, but not all three with each other, not all three, okay? Because maybe the teeth will not mesh correctly, and we don't care about the meshing of the teeth. Here, we don't care about the tool, where we care more about seeing this, the soil being eroded. This is what we care. Now, I would like to have gravity in order to have debris. So I will assign the gravity as default. I think the default is -z. -z, yeah. So the gravity will be like here. There will be particles falling down. I think we kind of need the tray to collect the particles, because if we don't have a tray, then we'll need to zoom out very much in order to catch all the eroded particles. Yeah, let's just see. So now the main load is a joint load, and it will rotate how many times? Will rotate for fun. Do we have a Tricone drill bit rotational speed? 50 to 125 RPM. All right, so it's kind of small given the fact that we are conditioned by the end time. So let's make it, you know what, 250 RPM, rotations per minute, and I would like to convert it to radians per second. Come on, give it to me. 26.18 radians per second. The problem is that I would like to have 0.1 second as end time. So, can I dream of having 0.1 here This means the joint load being instead of rotational velocity, this load should not be only revolute, but also it should go inside. So maybe a cylindrical joint. Look here. With the cylindrical, we also have the rotation and the translation. This means we do have this rotation. Let's assign the default that they advised. 26, yes, radians per second, to have 250 RPM, which is pretty fast, pretty quick. And let's also go inside. How much should we go inside? With this thickness. This thickness is more than 500, yes? 750, oh. Let's go with 500. Let's not push it too much. Duplicate, and here we're going to select Z displacement and displacement. Tabular time and minus how much? 500 millimeters. So I have two loads, yes? Penetration and the rotation. Once these teeth engage with the soil, naturally, by default, natively, they will begin to rotate, because they will mesh here. Normally, this is my thinking. I think this is how the assembly works. Let's assign here something like this. Also here. Switch to automatic mode and some default values here. All right, we have this, gravity. Yes, I think the solving time, we need to work here with the solving time. Here, let's go for 1e minus 7, but I think we will need to decrease it 10 times. Out of curiosity, I would like to review a little the options for the SPH. Minimum time step, max minimum density factor, density cutoff option, limit density, minimum velocity, radius cutoff, minimum strain rate cutoff, detonation, it's not related to SPH. Erosion control, this is interesting. Let's make this, I don't know, maybe 1, you know. Retain inertia. Now output controls result number of points 100. Save. How many hours will it take to solve? Starting as of material, so density must be defined. Why not? Let's define a density. Limestone. I'd like to have this page, limestone density in kilograms per cubic meters. Almost 3. However, porous or weathered. The density of solid natural limestone from 2. You know what? 2800. This is what I will give. Sandstones. Density. Limestone, I said. Okay. So density, double click, 2800 from my side. Save, go here, right click materials, refresh materials. Right click solution, click clear generated data, yes, save. And solve. Yes, very nice. Now the the usual, but the boundary conditions are correct. Do we have any question for Dennis? No. Perfect. What audience? Ah, we have 2 people. Hi, audience. Just 10 hours. So, and increasing 11 hours. All right. So now let's see what we can do. Let's stop and duplicate this because we know that we have a working scenario, even though it takes very much, all right? From now on, we're going to shorten somehow this scenario. So now the duplicate should appear, this one, and I can write this here, 10 hours solving time. This is the default, all right, for the starting of the simulation. Let me watch my smartphone for a second. Okay. So now, decreasing the node count. What is inside here? Yes. Yeah, let's increase the SPH size. If we make it 60, we have a node count of 22,000. 16,000. No, let's go even more. Hmm. 70. Something like this. I don't like the fact that it's beginning to kind of resemble the space between the teeth, you know, and yeah, it's a little exaggerated here. All right, we have this one. The other thing that we can do is because the meshing changed, we need to redefine these name selection, these named selections, something like this. Mode, box select, and I will change cursor mode to node, and I will select these nodes. And selection. And here we are going to choose selection. All right, now what can we do is, here instead of 0.1, we can make it, let's try from here. 1e minus 6, this meaning maybe we need to increase the maximum part scaling to 25. Let's see how many, maybe 3 hours of solving, maybe. Let's see. Of course, we need to have live results, you know, this is a live stream. Oh, so generous. Yes. And if we increase the rotational speed, let's make it maybe half an hour, maybe. So I said increase the rotational speed. How much? 26. 52. Let's double the speed. The displacement remains the same, and here I can make here 0.05. Again, I need to change here to 52 and minus 500. This will cut the solving in half, maybe 45 minutes or something. And if it goes correctly, we can solve half of the simulation if the trend is correct. Okay. Yes, and then I will continue solving offline, no problem. But I need to ensure that at least the beginning of the simulation is correct. I mean, the particles should erode as expected. Yeah, 48 minutes. 45 is okay. Okay. So while it's working, let's go again here and let's look again and see what other people have done. So here is the liquid removing the debris. Do we have here something like FEA? So but no FEA? Drilling, for example, drilling FEA. But not this. Even though it looks nice. Yes. Not this one. This one. Something like this one. No drilling, no boring, no. Instead of FEA, can I write simulation? "52 minutes. Is there a tendency? Are we somewhere? Yes, we're in the beginning. All right. So if you don't have the patience, feel free to skip where you see the results. I'm talking for the people seeing this after the live session. So it's a good thing that I'm working with this simulation because I don't see it made. I don't see that it is made boring. All right. the other meaning of boring. The cleaning fluid. Seventeen years ago, when Cosmos was a thing, there was a street of finite element analysis software, which was adopted in the SolidWorks environment afterwards. Yeah, it's a good thing that I'm doing this simulation. Come on, show something in SPH. Here, let me see if it touches. Oh yes, it touches, it began to touch. Oh yes, yes. Yeah, it's a start. Yeah, very nice. All right. Lots of Chinese manufacturers. And this comes from a machine. Yeah, lots of water needed. What is converge? Yeah. Lagrangian parcel modeling. What is this? Oh, it's very interesting. Liquid parcels. So the particles. Yeah, very important for specialists. So feel free to skip ahead where you see more results. Should I increase the velocity? I was thinking about decreasing the thickness here. Maybe make it half here. Also decreasing a little from the sides. Let's make a section view. I would like to inspect the mesh inside. It's pretty coarse. There are some interference, but I think we don't care. We didn't assign interaction between the tooth, the tools and the mainframe. It's as coarse as possible. Yeah, let's quicken a little the solving. The camera keeps falling. Where are we here? The rotation is too slow. Too slow. So let's make it faster. Do I interfere with the soil or not? Yeah, let's decrease a little the soil thickness. Here I can say that it takes around 50 minutes. And here we can duplicate. I can remove the frame that I made around on the periphery of the soil. I can remove it because we succeeded in fixing the outer nodes. I will go and get I will look a little on my smartphone. Please excuse me for a few seconds. So let's decrease the thickness of this soil portion. Something like this. Let's move it more here. Yes. And do I need this chamfer? Or do I need this portion? What happens if I delete this? Oh. All right, let's leave it as it is. And I advised on decreasing here. No much. How much should I? Something like this. Let's save this as version 3. And right-click, update geometry from source. I will also double the rotational speed on the frame, the main frame of the tool. Pay attention that always it assigns default fixed joints or bonded contacts, but we don't have contacts. Just pay attention. All right. Yes. On soil, how much was it? 70. If I leave it 60, how many nodes will have? 10. 10,000. Let's work with this, and let's again apply the fixed boundary condition. Box select, right click, cursor mode, node, and we're selecting here. Yeah, we're referenced in the SPH, the particle bodies are meshed with these centers, not spheres. So what is important is the center of the sphere. And selection. And here we are selecting selection, if we can say something like this. So I said maybe go here towards 0.025, and here instead of 52, let's make it 100. And here let's make it 250. Minus 300, okay. It was rotating too slow for my taste. Oh no, oh no, 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 no. It's a good thing that I saved the version 3 of the geometry. Anything from the vast audience of 0? Nothing. Yes, we lost that. Let's close this and open again. So there was a message from someone, but they deleted it. No problem. So what happened here? So here I am going to import V3. All right. Let's see on the model what we need to do. We need to wait for space claim to open behind doors. Then the geometry will be imported here. So let's see. Save. Do we have kept? All right. Virtual topology. Let's delete and remake it again. Of course, fixed joints. The body interactions are correct. I said, and the default there, generate mesh. Let's create the name selection again. Box select, cursor mode node. And selection. And here we're choosing selection. All right. So I wanted to have here 0.025, the rotational velocity to be 150, and the displacement minus 300. Save. Come on. Why do you do this? Yes, can we make it half an hour? Or even 50 minutes? We can. Just out of curiosity, what is the price for such thing? Limestone, what? Price list. Oh my God. So expensive. This is around $5,000, $4,000. $3,000. This is less expensive. Of course, it depends on the size and the materials. On the hardness of the soil, the rocks to be cut, of course. So are we on the right direction? I have a good feeling. Yes. Yes. We're definitely where we should be. It looks so nice. Yeah, too nice. Cohesive soil. Oh. Yeah, I would like to simulate something like this. It's very nice. The liquefaction of the soil. I don't know what it is, but it looks very nice. So nice. MSC Ditran, yes. Oh, so nice. So nice. Oh yes. Such high stress in soil. I should have looked more on the definition of the material. But yes, it's beginning to look a lot like we expected. I would have seen to. I would have wanted to see this tool buried inside the SPH part, but yeah. Ah, I forgot to fix here the back, the back of the soil part. I think I needed to fix it. Otherwise, it will make a sag curvature here if I don't fix it. But yeah, let's go with what we have. So nice. Tree uprooting. Oh, so interesting. I need to also make such a simulation. Let me write it down. This should be interesting. Oh, so nice. Mm. Yeah, very nice material properties here. What is podcast? Okay. It's like a support, like a fixture or something for the pillars, for the columns. This is a sorting device. All right. Yeah, this is very interesting. Very nicely simulated. Very nice. Yes. And explosion inside. Okay. This is doable. This is not hard. What is this? With what software? What software? Yeah. It kind of stopped. 10 step too small. Total velocity and stress and strain, but only for the soil. Is it possible? Yes. Rotational speed too small. Why do I have this subarrow times that too small? Maybe there is a problem with fixing the soil on the periphery. Maybe there is a problem with this. I didn't allow the periphery of the soil to displace, and maybe there is a problem. I'm forcing the solver too much. Let's give it another trial very quickly, and yes, we'll close this simulation. This is a start. It's a good start. We just need to refine. Save. Duplicate. I would like to increase the rotational velocity of the tool. Let's increase it to 300. And did I delete the support of the frame? Yes, I deleted it. Let's do something like this. The edges, the corners, are never affected by these tools. Let's fix only the edges. Box select. Cursor mode node, and I will catch only the nodes on from the edges, these nodes, you see, because they will not be touched by the tool. And name selection, yes. And here I will choose name selection, yes. I don't know if I should go smaller with this. Why not? You know what? 500. I'm thinking about how the teeth will find the spheres. Let's see. What channel is this? It's like a settling of soil due to the gravity, I think. So nicely done. Oh, Drucker Praga extended soil model. ANSYS. SPH is the SPH used in LS Dyno. We're half into the simulation. Let's see. Yeah, I kind of predicted something that I should have fixed maybe the auto. I predicted this curvature because I need to compress the soil. Yeah, it looks very promising. You know what? Let's let it end in order to have a solved start. Then I will fix the end, as I promised. This end, I would like to fix it in order to have compression here. Can I visually see the difference between SPH and them? Let's see. Yeah, these are separate bodies. This is the discrete element method. So this is one fluid, one body, SPH, or particle body. This is one fluid, and these are, each sphere is a separate body, a discrete body. Yeah, very. Yeah, in reality, there is the other side of the soil, the real, which presses, opposes the drill. These can be two SPH models. So a very fine size particle body with very small distances between the centers, and the big body, big SPH size, and they will diffuse. So this is water, yes, and there is soil, and it's creating waves. Okay. This is interesting to simulate. Don't know if you see it, something like this here. Come on. Oh. This means that the displacement is too much. I think I can rotate no matter how fast, but the displacement is too much. Maybe we should make it half, maybe. So here we have fraction. Fraction because we only fixed the edges. Yeah, the problem is more complex than I anticipated. So you know the trick here, we're going to show undeformed model. All right. One last trial with the backside fixed. Any question from the audience? Yes, there is a question. Good work, thank you. Thank you, Mr. Hassan. I'm trying to solve a water entry problem. Firstly, interrupt the water from the main pipe. Then call someone. Don't stay in the water, especially if it's cold outside. All right. I said less displacement, minus 150 maybe. And let's fix here box select, mesh, cursor mode, node. And let's fix this backside and selection 2. And here, let me duplicate and I will select selection 2. All right. So I fixed this. Come on. Yes, I fixed the backside, yes? Yeah. You understood. Yes, 150. I don't know if these edges are enough to fix what I have here. Let's go with this. Let's see, yes. We should have a compression. Rotary spader interacting with soil using EDEM. So nice. Many SPH layers. Ooh, so nice. Oh, yes. Yes, yes, yes. Even though it's not SPH, it's a discrete element method. These are chips, gummy bears. Yeah, it's nice to visualize the wear. Very nice. This is an FEA that I like very much. Tell me we're good. Hopefully. So I like to see the crushing of these separate of these discrete elements. And now this can be done also in ANSYS because ANSYS purchased Roque. So, but this is not SPH. This is DEM. Some examples in ANSYS Roque. The MCFD coupling. Let's see this. So nice. Yeah, lots of parting here with nuts, beers, and chips. Yes. I think also we need to edit this value for the geometric strain limit. The rotational velocity is still too low. So what will happen? I will resume in a future live stream this problem. In the meantime, I will make it decent to behave. And yes, for the moment we'll accept what we have. This is the beginning. The procedure is correct, only we need to work on and optimize the parameters, the process parameters. Also the sizing of the SPH and, as I said, the geometrical strain limit. I'm constrained by the end time because it's too small. And in reality, we only describe five radians because we have a hundredth of a second. Yeah, 5 radians, which is too small. You know what? Let's dictate here instead of rotational velocity. Let's dictate rotations. How much? How many? I was thinking about 5 rotations. 5 multiplied with 1800. 1800. Minus 200. 5 rotations. 1, 2, 3, 4, 5. Let's see. Yeah, I should have went from the start, from the beginning, with applying the needed degrees, not velocity. The solving time increased. We don't care too much as long as the behavior is correct, because I can finish solving it offline, but at least I'd like to run it for 30–40% of the simulation. Oh, well, do you know, it doesn't work. It's too fast. The shock is too high. All right. 1 second. Isn't the frame rigid? Yes. hide others. Save and solve. Now I know for sure that we will have no debris between this and this, so I can delete it, no problem. Come on. Why are you doing this? How long is this live stream? 2:25. We're approaching 2 hours and a half. So how much does it take? 20 minutes. Grinder. So nice. So nice. Superb. This is superb. Oh, too high speed, yes. Come on. How much should I give? One rotation? So little? Control S and solve. Maybe I overkill the definition of the revolute joint. Oh, so nice. It looked like an abrasive cutter here. All right. Is it working or destroying again? It is doing something. It has the tendency of destroying us. You know what? Let's also make these cutters. Let's make them rigid as well. All right, we need to remesh. We need to redefine the name selection. again, and let's hide all other bodies. Box select. Cursor mode node. Yes, and selection. And here we are choosing selection. Everything is kind of fixed. All displacements are fixed, all right. Rotation 540. Yeah, let's leave it like this. I don't know. Yeah. So everything is rigid except the soil. Less than 1 minute. We like it. So I should have started with rigid, then make it flexible. I should have stabilized the simulation. See that it works, and the soil is compressed correctly. This is what I should have done. Oh, it looks so nice. Finally. So let's do it for a few minutes. This is 1 minute. Yes. Finally something working. All rigid except soil, of course. 50 seconds. 50 seconds is a good solving time. Any question from the audience? No. Come on. Let me grab some water. Hey, tether machine simulation. This looks promising. So let's keep what we have. So let's make this 0.05 and I will multiply 5 times. 2700 700. All right. And the displacement 150. Come on, we should have something good. If I don't like how it looks like, then I will need to decrease the geometry strain limit towards 0.5. Three minutes. Finally, it's lots of rotations. Finally. No debris, no spheres flying, falling or something. At this moment, they're just being compressed. Ooh. Ooh, it looks so nice. We have something. Oh my god, the values of stress. My god, oh my god. Yeah, and I will rerun this with 0.5 here. Finally, we have the beginning of a hole. Now we have a particle maybe which flew in the cosmos. Here, this is the particle. This is why we don't have values there. Yes. Yeah, very nice. Finally something, a good basis, finally. The soil materials needs optimized because of the high stress, which is output. Let me remake this to 0.5 geometric strain limit, and we can close this live stream. Let's animate just a little. Yes, and of course we can always make a section view. This one is this section view is suitable to see the tool. Is it suitable to see the drilled hole? Let's see. Why not? Yes, and let's remake it to 0.5 geometric strain limit, then we can geometric strain limit equals 1 here, and here I will duplicate to make it 0.5. Any question from the audience? Hi, bro. Manik Antabe Javada. Hi, bro. Yes, we have a salutation. I said, let's make this 0.5 and rerun the FEA, because in principle, it takes 3 minutes, in principle. In practice, I think it's closer to 5 minutes. We can accept 5 minutes for solving, as long as it's not 1 hour. Details and 0.5, I said. Control S, solve. I was thinking of maybe moving a little. Should I move? Maybe moving the soil another time, because it's a little on the edge. One of these tools is a little on the edge. So in principle it's 3 minutes, but maybe it will go towards 5 minutes. What is this? Raking efficiency can be evaluated by measuring the height backing. It looks so nice. Yes. Tether. Solver is decay, impinging, jet cooling. Another sorter. Vibrating screen, yes. Python. Pipe erosion, yes. Where are we here? 60%. We do have some debris, and I think maybe it follows the gravity. Does it? No. the gravity is minus z, and does this fall? No, it doesn't fall down. You see what I was talking about? I said maybe this soil body should be moved because here it's on the limit. Yeah, it's also nice. Let's let it solve, and we'll successfully close this series of simulations. So the geometric strain limit doesn't say too much, it doesn't influence too much the simulation. Good to know when using particle bodies or smooth particle hydrodynamics. Okay. What is this? It's like a crusher or something. Even the grass is simulated. What we have seen in the past, but from another perspective. I think it's cutting of the grass. Oh my god, so nice. Oh, so nice. Oh, this is a peel inside the intestine. Large intestine, I think. Yeah, enormous possibilities. $28. Yes, I know. So we can successfully close this live stream. No other comments. Yeah, some errors inside the simulation, but at least we don't have high hourglass energy, internal energy is increasing, contact energy, yes, as it should be. So we're right. It's nice. Total deformation. So we can clearly say that this is drilling, okay? We're drilling a hole. Maybe we will retake this topic in a future simulation. So this is definitely drilling. Look here, it looks so nice. Yes. Of course, strain. It's exactly what we wanted from this series of simulations. So thank you for your attention, and meet you in the next live stream. Bye-bye. Thank you.